So today's lecture is all about a specific point and the corresponding optimal condition. So how these two concepts would be related, we will discuss in detail. So recap of descent direction. So in last class I mentioned about relation of descent direction with sublevel set. You need to know the relation between sublevel set, and there also if you are having sublevel set, then what is the what is gradient? Gradient is always talking about normal to the sublevel set at a point. So it defines normal. Then if you are having a normal, then you have to discuss about tangent direction as well. So those kind of things we will discuss as a recap. Then I will go to discuss about various stationary point and the relation between a stationary point and optimal points. I will discuss in detail. And in next class I will discuss about optimality condition for various problem, linear program, quadratic program, and semi-definite program. Those kind of things would come. So in detail we will discuss various problem. So here, if you keep on changing problem, your optimality condition, it will keep on changing with respect to different convex optimization problem. So those things we will discuss in detail. And here, whatever problem we will discuss, everything problem would be convex in pattern. And in next module, duality, where I will see, we will discuss in detail about how to convert non-convex into convex, and then we will go for further solution pieces. So coming to recap that descent direction. So in order to understand descent direction in better, you need to know level set, sub-level set, and tangent direction as well. So I am defining it here again. So suppose you are having objective function, or simply you can say that your function from Rn to R. Suppose it is differentiable over Rn, and we define the following two important set. First set we are calling it sub-level set. What is that? It is always in the domain of the function. So sub-level set would be a subset of domain. It is in Rn. Domain of this function is Rn, so it must be Rn. So it is collection of all the point of the domain point, all the point from domain of the function, such that f of x, the value of function is less than equal to a particular given number alpha. So it always defines a sub-level set, and this sub-level set, it happens to be closed. And also in case of convex, it is taking very nice structure. It happens to be a disk kind of a structure. If function is function of two variable, then sub-level set always take a disk pattern. Now, once we are having sub-level set, with respect to this, also we can define a collection of unit direction at a fixed point. Fixed point. We will take point y. So here we have taken alpha arbitrarily. Now, in case of defining direction, so direction, in order to define direction to sub-level set, we have to first take a point from the domain itself. And from with respect to this point, suppose this point we are calling it x bar. It belongs to domain of the function. Then definitely the function will take some value. Uh, that functional value we will call it f of x bar alpha. So it is a fixed real number. So call it f of x bar. So call it alpha. Take it as alpha, as a real number. So it is a real number. Now with respect to this alpha, you will define a sub-level set. So that sub-level set we will call it S of f of x bar. So it is again, is this notation is for sub-level set. That means it is a collection of all the domain point such that f of x is less than equal to this specific alpha. That means alpha is the image of x bar at point x bar. So with respect to x bar, we are defining this sub-level set. And tangent at point x bar, we will take. So it is a what? It is now a part of domain sub-level set. So at this point x bar, t of t of fx, tf of at x, it is collection of all unit direction at point x bar. It is talking about. So suppose you have a function of two variable. What would be your sub-level set? What would be dimensions of sub-level set? So if you are taking function of two variable, then your sub-level set would be a domain. So this kind of it would be a this kind of thing. So this one is a sub-level set. So if suppose you are this point is x bar, this point you have taken x bar. With respect to that you define alpha, and correspondingly you are getting this one is your call simply. What is this one is your sf at point sublevel set defined by f at point x bar. So this is the sublevel set with respect to f at x bar. Okay, so we are getting sublevel set. Now here we will talk about for this 2D disk. What is the how many tangent vector you observe here? Samdeep, any answer? How many tangent vector here you observe at x bar? Ankit, Ankit,
Yes, sir.
how many tangent vector you observe at sublevel set?
Can you repeat, sir? आवाज कट के आ रही.
I'm asking that how many tangent vector you observe this with respect to this sublevel set define with respect to x bar. That means here x bar is here. So how many tangent vector you observe?
Sir, at a point
Okay,
only one.
there would be two unit tangent vector. One would be this direction, in this direction, another would be one, and it will be opposite.
Oh, okay, sir, I thought that is a single line. Okay, okay.
No, here your point of reference is x bar.
Yeah, sir. Okay.
So that's everything talked about with respect to that point under consideration. Also, whenever we are talking about direction, direction is always a ray. It is not a two-dimensional kind of things. So always we define direction with respect to a reference point. So it would be a ray kind of things. But this S is defined in such a way it is a unit vector, because you know that if you are having a vector, then what is the best way to represent that vector with respect to direction? Direction how you find? By dividing the norm of that vector with the vector itself. Then we are getting unit vector. Unit vector generally in +2 you might have already seen that unit vector is always represent direction of the given vector or given line. So that's where unit vector criteria is coming here. So we are having two direction. Now next property. So these are S. So in if your function you are dealing with function of two variables. Suppose you are dealing with function of three variables. How many direction you will observe? Swamitip, Swamitip, are you present? Okay, then reply. How many direction you observe in case of function of two variable? No, three variable. If you are having a sublevel set with respect to function of three variable, then how many direction you will observe? No. Okay, Sujit, you reply. Sujit Maurya.
Yes.
Are you active? Okay. Are you able to listen me?
Sir, your voice is breaking.
Voice is breaking. Okay. Are you able to listen question or not? I asked that how many direction you will observe when you are having a function of three variable, and with respect to that you are defining a sublevel set. Okay, there will be infinitely many, because in case of 3D, what you will get your sublevel set would be a solid sphere. Solid sphere. It is difficult to draw. So not ellipse. Solid sphere kind of a structure would be there. So if it is a 3D disk in 3D structure, or simply solid sphere, if you're taking at this point, so you will observe infinitely many directions. So there would be infinitely many S. For this set would be this set would have infinitely many elements. So that is the idea. So all these are S. All these are S. So infinitely many S you observe in case of 3D sublevel set. So this one is 3D sublevel set. Here X belongs to x bar belongs to R3. R3 intersection at sublabel set. Please sublabel S alpha, SF x bar. But in case of this example, your x bar is coming from again SF x bar, and it is actually two-dimensional disk. It is a subset of R2. So in case of R2, this set of unit tangent direction, it is having just two element. Call it S1. Second one is S2. But in case of here, you are having infinitely many possibilities. There are infinitely many possibilities. So that's where this is the picture of TF at x bar. Now there is one important condition. It says that if you take any direction from the, call it tangent set, better name would be tangent set at x bar, unit tangent set at x bar. So if you're taking S is a unit tangent vector at x bar, then if you take the inner product with the gradient at that point, gradient will be definitely, it will be, what would be the, in case of 2D, what would be direction of gradient? It would be direction of gradient. And direction of gradient, you can observe that it is always perpendicular to the tangent vector at that point x bar. So that's way, if you take a dot product of S with gradient at point x bar, it would be always 0. It would be always 0. Proof I have already mentioned there. No need to go detail in proof. From the geometry, easily you can observe that proof. So all proof I have already derived it here. You can look into, if you find interesting this one, then you can look into this proof. It is very compact proof is given here. This proof is taken from Nastro book. If you are willing to study optimization in more detail and in a really fascinating way, then you should visit Nastro book. And Nastro is that very complicated kind of book, in sense that it will take time to understand that book. So I'm coming to descent direction. So what does it talk about descent direction with respect to gradient also? So I had already mentioned that what is descent direction it is talking about. So you had already seen that in 2D, S was what? S was a tangent vector. So with respect to tangent vector, or you can simply say that at sublevel set. So if you're taking this one is the 2D sublevel set, that means disk in R2. So it is a sublevel set with respect to x bar you are defining. So I had already mentioned that here you are getting a separating hyperplane, which is with respect to this sublevel set, separating hyperplane. And what was the separating hyperplane? It was the projection of this linear function, projection of linear approximation of the function at point x bar. So linear approximation, we write it like this way: f of x bar plus inner product of gradient with any direction, gradient of f at point x bar So this famous hyperplane, you know that it happens to be a tangent plane. It is a tangent plane at x bar on the function. On the surface, it just support the function. But if you project this tangent plane over the domain, then it will becomes just a line. This kind of line. For remember that here I am talking about function from f is from R2 to R. Simple, for better visualization, we are taking this scenario R2 to R. So this one is, you can call it, it is a H dash, or so H dash, it is defined by what? It is defined by, you can take equivalent dot product of gradient gradient. Here take dot product of gradient with y minus x. Or simply s. Here take it using the last result what I had told that. So take tangent directions. Better would be tangent direction as I had taken. So take dot product equal to 0. This will define your hyperplane. Hyperplane for the here separately has or supporting hyperplane for this disk. And here descent direction would be all where dot product of gradient with t is less than half of this hyperplane. Here, if you take any d from here, this d, this take this d. So this d, if you're taking dot product with gradient, then that would be definitely less than infinity and less than 0. So these are coming with respect to this negative half space, negative half. So this is the geometrical visualization of so you can say that like so this one is your supporting simply call it tangent plane at x bar. Suppose this point is on the graph f of x bar comma x bar, f of x bar. It is a point on the graph. Okay, so this one is the tangent plane at this point, and if you try to look into the contour, then suppose x bar might be somewhere here. Here x bar is here. So if you project this tangent plane, then it becomes a line, and it will be what? It would be tangent line to the this disk. This disk is the what is name of this disk? You can name this disk is your S sublevel set of with respect to f at point x bar. Call it. This one is the disk. Here you define. And what are the descent direction? All these direction are descent direction. All these direction are descent direction. These are the descent direction. So you can say that these are descent direction. And if I ask what is the steepest descent direction, if your norm you are taking 2, then this is the steepest descent direction. That means what is name of this one? This one is the negative of the gradient. Suppose this one is gradient. Gradient is always normal to the sublevel set. In previous slide, I had already expressed that, and this would be a steepest descent direction with respect to 2 norm or Euclidean norm, we can call it. So this is the steepest descent direction. That means you will observe a very fast minimization or decreasing of function along this direction. So this is, you can say that this is the best descent direction. You can say that. Apart from that, these all are also descent direction. There are infinitely many descent directions. You observe that. So this is the pattern of descent direction, and with respect to gradient, you are getting a steepest descent. So all these are descent direction. So I'm coming to discuss. So this, if you are taking this one was the scenario of convex problem, and this one is scenario of non-convex problem. I will go to discuss about various accessory point. What are those? So first I will discuss about first order accessory point. That means first order means it is dealing with gradient, and second order means that would also involve Hessian. Apart from gradient, second order accessory point will involve Hessian as well. But here when we are calling it first order accessory point, then it is just involving gradient. So first order accessory point of a function from Rn to R, it satisfies the condition that at first order accessory point, if domain of the function happens to be complete R, then first order accessory point satisfies that gradient is equal to 0. Remember that the domain of the function is what? Complete R. If domain is not complete R, then we can't say that gradient would be 0 for being a stationary point. And because at boundary point there would be non-zero gradient. So your domain of this function is Rn, complete domain space, Euclidean space Rn. So that's why this problem is unconstrained problem. So the criteria for being first order association point is the vanishing of gradient. If the gradient is vanishing, then simply we can say that that point is a first order association point. Now, once we are having a first order association point, then we can't say that point would be whether that first order association point. It may be a local minima, it may be a local maxima, or it may be a saddle point. So these kind of things observe that. And also, if you try to talk about stationary point in terms of direction, you can say that a stationary point means that there are no feasible direction at the stationary point x. If x is a stationary point, that means the gradient is already vanished there. Then we simply can see that in a small neighborhood of x, so there is no feasible descent direction. There is no descent direction. So this kind of scenario you observe. So here, this is the stationary point, and what you observe here, here you observe that there is no descent direction. So if you go in this direction, what will happen? Function will increase. If you go in this direction, take update your x in this direction, then again function you observe the function is increasing. That means at this point we are unable to observe any descent direction. So I have given many picture of first order stationary point. So first, if this picture you can observe that it is this kind of stationary point we are calling local minima. What is happening if you are at this point and you proceed further, either here it is one dimensional function, so there would be two descent direction. So one is from right, another one from left. So it would be something one from right, another from left. So if you try to, so there are only two directions. So if you try to approach this, if you go away from this point towards right, what you will observe, you observe that function value is increasing. Also, if you go towards left from this point x, then again you observe that function value is increasing. That's why this point is what? This point is a local minimum. And similarly, if you come to here, if you just deviate from this point toward left or right, what will happen? So function value will increase. So that's here in this case, function value will decrease in both side, either in left side or right side. So that's why this one is this first order point is a local maxima. Now, if you come a point like this way, here what you observe that. Here there is change of concavity as well. After this point there is change of concavity. Here what you observe, concavity is up, then after that there is concavity changing down. There is a change of concavity at a point. That means it is talking about a situation where gradient second order derivative also may be zero or maybe indefinite sign. That means either two scenario may come here. Either it will gradient second order derivative zero or second order derivative indefinite. That means we can't say whether it may be positive or negative. In that kind of situation, we are getting point of inflection, or in two-dimensional case, we are getting saddle point situation. So those things will come. So a convex function may have only one first order stationary point. So if you are talking about convex function, then convex function can't have this situation. Maxima you can't get, and minima in this saddle situation you want to get, because regarding I'm talking about convex function with respect to minimization perspective. I'm not talking about maximization. Here our optimization problem is all about minimization problem. So here in case of convex function, we will have only one kind of a stationary point, that would be minimum stationary point, minimum or minima, local minimum. So whereas if you are taking non-convex problem, then we will have a very trouble situation. That means that a stationary point, first order stationary point, it may be a local minima, it may be a local maxima, or it may be a point of inflection in case of function of one variable, or point of or saddle point in case of function of several variables. So this kind of situation is coming. So that's way it is not easy to deal with the non-convex problem. There you need to go for some specific technique uh, and some specific problem you can solve uh, based on you have to be very careful while dealing with non-convex problem. So that situation is coming here. I will talk about few example of first order point for unconstrained problem. So we are taking unconstrained problem. By default, that means domain of the problem or constraint state is Rn. Here I am talking function of two variable. So our constraint state is R2. So in 2D, a convex function x square plus y square, it has first order accessory point, and that would be a global minima. Global minima. Why? Because x square plus y square is a convex function, and in convex function, every local minima is a global minima. It is a convex function is having only one kind of accessory point. That one is local minima, and also we know that local minima is a global minima in case of convex problem. So that's why it is directly. It will talk about global minima, or you can directly talk about global minimization of a convex optimization problem. So a minimum from every direction. That means from any direction if you're coming, so your accessory point would be the global minimum. So this is the situation. You can observe that. So this one is a convex optimization problem, function of two variables. So if suppose if you are here, then definitely if you descend it, you will where you will reach at this global minimum. And if you take another function which is non-convex x square minus y square, it is a non-convex problem. So for this function, definitely apart from minima, we may have saddle point as well. So this is the scenario. Origin is a this point is 0 0. So origin is a saddle point for a non-convex function x square minus y square. So here in non-convex problem, what you observe that in one direction we see there is a decreasing of function, increment of function, and if you proceed in another direction, function value here what decreasing it is happening. So here concavity, there is change in concavity. In one direction we observe concavity is up, in another direction we observe concavity down. So concavity down. So that's why this situation is a saddle situation, saddle point situation. If you take a, so this saddle point is also a first order point, but this saddle point is not a local minimum. So it is, so saddle point situation is coming only in case of non-convex problem, not in convex problem. In convex problem, we are having only one kind of saddle point. That one is local minimum. So what is happening? First order accessory point in general, that means for non-convex problem, may not be a local, may or may not be a local minimum. If you are having first order accessory point, you directly can't say that that point would be a local minima. That may be a local minima or may not be. So for a non-convex F, a first order accessory point may or may not be a local minima. One example I have taken it. Again, this example is coming from Nastro book, implied from Nastro book. So if you are taking a function which is defined by 1 by 2 into x square minus y square. So what is happening? 1 by 2 is coming just for simplification, that when you will find gradient, so 2 factor will come, so 1 by 2 and 2 will cancel out. So if you are willing to find a accessory point of this one, how you will find first order accessory point? So find the gradient at point or to 0. If you take 0, so what is f of at 0? What is f of 0? F of 0 is 0. So that means if you're taking a neighboring point in the neighborhood, a small neighborhood of 0, and if 0 is a local minima, it will say that a function is taking least value at 0 in the neighborhood, a small neighborhood of 0. So we don't find any function x such that that would be greater than that would be less than this f of 0. If you are unable to find that point, then we will claim that 0 is a local minimum. But if there exists, if it is not true, that means it is not true, at least for some x, then we will say that 0 is no more a local minimum for the given function. For some x, if you try to find some x with respect to that, uh, that this inequality is not holding, then we will say that function is not a local minimum. So also you can calculate the Hessian. Hessian would be indefinite here. In order to establish first order derivative, you don't need. So we are going to calculate value of function in the small neighborhood, a very small point near to origin. So if you're taking epsilon very small, that means a small positive real number, then definitely epsilon by 2 and epsilon it would belong to the neighborhood of 0. It would be in the neighborhood of 0. Definitely this point would be in the closed neighborhood of 0. Even you take with respect to epsilon, there is no issue. Closed neighborhood, closed disk, we are taking around 0. So it would be in the neighborhood of 0. So try to calculate the value of f at this point, epsilon by 2 and epsilon. So what would be calculation? Through calculation, if you substitute x1 equal to epsilon by 2 here and x2 equal to epsilon, and then after simplification, you will come across that this function is taking value minus 3 by 8 epsilon square. And what you observe that epsilon is a positive number, epsilon square also it would be positive number again, but here we are having a negative sign. So that's why it is a negative number. That means f is taking negative value at this point, but at f0, f is taking positive value. So this quantity is strictly less than f of 0. Then simply it signifies that 0 is not a local minimum. Despite of being 0 is a first order accessory point, but it is not a local minima. And now, then what kind of thing it would be there? So you have to look for Hessian. If Hessian is infinite, if you try to find Hessian of this function at 0, what is Hessian? 1, 0, 0, 0 minus 1. So here you can observe that this Hessian is neither a positive definite nor a negative definite. What is that? It is one eigenvalue is 1, another eigenvalue is minus 1. So it is having two opposite sign of eigenvalue is having two opposite sign. Simply you can say that it is indefinite matrix. So that's where this point x equal to 0, it is a saddle point. So you have, it is a first order accessory point, but it is a saddle point. Plot you can observe like this way. So it is totally algebraic description of saddle point or first order accessory point. Totally algebraic definition. So you come across this one is the saddle point. Another plot I have taken it here. So if you are taking a function, again a quadratic function, minus 2 times x1 square plus x1 into x. It is more than quadratic, it is cubic also you can say that. X1 into x2 square plus 4 times x2 square. Then if you try to find a first order accessory point, then this function is having many first order accessory point. One first order accessory point is this one another first order accessory point here, here it would be here. So this point is a local minima, this point is a saddle point situation. So many different kind of saddle point you are. So this you can observe in the contour plot. This one is the surface plot, this one is the contour plot. Contour plot always give a vector visualization of optimal point, because you are here already interested to find optimal parameter of the machine learning algorithm or whatever model you will take. So you are interested to find optimal parameter. So that's way. So optimal parameter, that means you are finding optimal value in the feasible set. So this is the feasible set. In this feasible set, one local optimal is this one. This another is first order accessory point is this one. Another first order accessory point is this one. So here you can observe that you can characterize various kind of things. So if you coming to this point is behaving like local maxima, this point is local minima, and this point is saddle point. So you, for this example, you are getting all three kind of first order accessory point by solving the equation that gradient of f equal to 0. If you solve, then you will get all three different kind of first order accessory point with respect to this function. Now, something more about the saddle point. We will talk about with respect to eigenvalue of the Hessian as well. So, if suppose your Hessian of the function it is a constant, then it will be easy to find the eigenvalue of that Hessian, because we know that Hessian is always a symmetric matrix. So, if the eigenvalue are mixed, that means the eigenvalue of Hessian are either positive. It is positive and negative as well, and but non-zero. If there is no zero eigenvalue of the Hessian, only we are having positive and negative eigenvalue of the Hessian, then we will get a saddle point, and that saddle point would be a strict saddle point. In the saddle point, also there are two classification of saddle point. One saddle point we are calling it a strict saddle point. Another one is non-strict saddle point. So in strict saddle point, what to observe that the graph is concave. You can observe that the graph is concave in this direction. That means concavity is down. Concavity is down, and another direction graph is convex. That means concavity is up. So in this direction graph is convex. So we can observe like this way. So there are two kind of curve we can observe for a function which is having a saddle point. So this white dotted line is a saddle point. You can say that. So another example I have taken it non-strict saddle point. So this example, if you take non-strict saddle point, then here this one is a saddle point, and you observe some flatness is coming here. It is not similar to last case. So when you are getting a non-strict saddle point, when your Hessian is degenerate, that means Hessian is having at least one eigenvalue 0. That means determinant of that Hessian is 0. That means Hessian is singular. If degenerate means simply you can say that Hessian, if Hessian become singular, then you will observe non-strict singular, non-strict saddle point. But if Hessian is always non-singular and having opposite sign of eigenvalue, then you can say that in that situation your saddle point would be a strict saddle point. So this is the example of non-strict saddle point. So one another definition I have discussed in term of eigenvalue of the Hessian. So if suppose your eigenvalue is every eigenvalue, your least eigenvalue. So what is observed that in linear algebra I might have discussed that if you are taking a symmetric matrix. So if suppose Hessian is a symmetric matrix, so that means Hessian is belongs to Sn, class of all n by n symmetric matrices. So if you are taking a Hessian, and what is happening, it is a symmetric matrix, and if you are going to find eigenvalue of that symmetric matrix, then eigenvalue always you can put that you can do a sorting. Always you can write in a proper ordering. That means largest eigenvalue is lambda 1, then next largest is lambda 2, likewise, and finally you will get the least eigenvalue. So always you will observe a proper sorting of eigenvalue in case of symmetric matrix. So you observe your Hessian is symmetric, so that one is already guaranteed. So if suppose your minimum eigenvalue of the Hessian is greater than 0, that means if minimum is greater than positive, that means every eigenvalue of the Hessian is positive. Then this one is talking about local minimum. Local minimum, very nice situation that we are always willing to see. Now, suppose it happens that some degenerate case is coming. That means your Hessian is having at one, that minimum eigenvalue is 0. Minimum eigenvalue 0. In that case, what will happen? So that point may be a local minima. So how you can establish? You can establish this local minima based on higher derivative. That means Hessian or tensor kind of approach. Third order derivative. Second order derivative is Hessian. Third order derivative is tensor. So with respect to that, you need to establish. You have to check to see whether that point is a local minima, or that point may be a saddle point as well. If it is a saddle point, then this situation is coming as a generally coming as a non-strict saddle point. Now, so when so here this one is a very probabilistic. There is a problem. This one is a little bit complex situation. Now, once you come to know that the minimum eigenvalue is negative, that minimum eigenvalue is negative, then it definitely it says that the function is having, or the problem is having a saddle point. Definitely it is having saddle point. And what kind of saddle point? This saddle point is a stick saddle point. It is a stick saddle point situation. We are getting a stick saddle point situation here when your minimum eigenvalue of the Hessian is less than 0. So you further call the saddle point in the last category where the minimum eigenvalue of the Hessian is less than 0. That saddle point we are calling it stick saddle point. And this one is, I told that this one is a very complex situation here. When your minimum eigenvalue is 0, then that point may be a local minimum or maybe a saddle point. So this situation I have already derived it here. So this one is example of stick saddle point. You can observe that here eigenvalue with respect to one direction you observe negative, and with respect to another direction it is positive. And this one is the example of non-stick saddle point. If you are having any question, you can ask. Otherwise, few more things I would like to discuss. I will take few more example. So first, before that, I would like to discuss about second order stationary point of a unconstrained problem. So second order stationary point of a function from Rn to R. What is that? Apart from satisfying the first order stationary criteria, it also satisfies second order stationary criteria. That means it says that a point would be second order stationary if gradient is already vanishes. Apart from that, Hessian at that point is positive definite. That means every eigenvalue is greater than equal to 0. So this one is positive definite definition of positive criteria of being a positive definite. So this one is also, you can say that you remember that in order to define second order point SOSP, so you have to satisfy these two conditions for being a second order point. Gradient must be vanishes at second order point, and the Hessian must be positive semi-definite. Remember that positive semi-definite. That means every eigenvalue is it says that one characterization of positive definite is that every eigenvalue is greater than equal to 0. Moreover, second order stationary point is a local minima. It would be a local minima if and only if your Hessian is positive definite, even something more than positive definite. That means even at point 0, we know that for positive definite matrix, what is the definition of positive definite matrix? So it says that if you define a quadratic form with respect to that matrix as a coefficient matrix, then it is greater than 0 for every non-zero vector. And if you take 0 vector, then what would be? If x is 0, then the quadratic form, it will take what value? 0. If you are taking x equal to 0. So this is definition of positive definite. But here what is happening? So second order stationary point, it will be a local minima if Hessian is something more than positive definite. That means irrespective of whether x is 0 or non-zero, Hessian is always positive definite. That means eigenvalue strictly greater than 0. So eigenvalue, every eigenvalue is strictly greater than 0. If every eigenvalue is strictly greater than 0, that means there is no 0 eigenvalue, then you can say that your second order stationary point would be a local minimum. So for a non-convex function f, a second order stationary point may or may not be a local minimum. So one example again we will see it here. So we are taking a function of two variable 1 by 3 times x1 cube minus 3 times x1 x2 square. So if you try to find this function, so 0 is a first order stationary point, and also it is a second order stationary point. Why? 0 is a second order stationary point. Why? Because we observe that gradient is 0. Also, Hessian at this point is positive semi-definite. That means at 0 it is taking 0 value. So it is a positive semi-definite. That means greater than equal to 0. Every eigenvalue is greater than equal to 0. So we can say that x equal to 0 is a second order stationary point for this function, but it is not a local minimum. How? If you find a value of function at a neighboring point of 0, that means that neighboring point take epsilon. So in the epsilon So definitely epsilon, comma epsilon. It definitely it would be a point. Even you take it's fine. In the small neighborhood of 0, then what you observe that at this point epsilon comma epsilon, value of function is taking -2/3 epsilon square. That means negative value, and this one is at 0 function is having 0 value, and this value is less than f of 0. So simply it says that x equal to 0 is not a local minimum. Why? Because this here the Hessian defined at 0 is uh, equal to 0. If it would be greater than 0, then we can say that then that time 0 would be a local minimum. But here in this case, it is not true. That means action at 0 is 0. That's why it is a just a second order ascending point, but not a local minimum. So plot you can observe it like here. So this is the plot of function 1 by this function, plot of this function. So you can observe that it is again a point, second order ascending point, but it is not a ascending point. So for a convex function, the Hessian is always positive semi-definite matrix at any point. So every first order ascending point of such function for convex function is also a second order ascending point. So for if you are taking a convex function, then first order ascending point is also become second order point. That means it satisfies these two conditions. For convex case, if convex case it is first order ascending point. Also, if we calculate second order ascending point, then also definition of Hessian convexity also defined with or simply you can say that second order characterization of convexity. It is talking about this Hessian is positive semi-definite. So due to that. You observe only one kind of ascending point in case of convex function. Okay, it is already 45 minutes. So other things I will discuss in next class. So I have already here discussed about various ascending point. This one is the first order ascending point. It satisfies this condition. A star is a second order ascending point. It defines in term of this. It is a very classical definition or definition with respect to neighborhood. And this one is fifth order ascending point. If satisfies this inequality, and X star is a local minima, means if the X star satisfy all these stationary for p equal to, up to p up to infinity. That means this scenario f of X star is less than equal to all these inequalities. So this kind of scenario is coming. This kind of situation is coming. So this is the criteria. So like that means if you want to say that first order you want to claim that X star is a point from X star is a local minimum point from a stationary point, then you have to establish all these order, first order, second order, third order, and that extra must be every order ascending point. Then you can claim that it would be a local minima. So it is a very difficult task to do that. We'll discuss other kind of optimality condition, other approaches as well. Okay, if you are having any questions, I'm going to wind up today's lecture. Regarding attendance, I have already created a link. You go and mark your attendance.